faithfully delivering value, interpreting great books from around the world. Hello, this is Sally Talks Books. Today we're discussing the book Tides, subtitled The Cosmic Surges and Wonders Stirred by Stars. Tides are the periodic rising and falling of the sea. Since ancient times, surging tides have sparked human imagination and appear in legends worldwide. Malaysian legends tell of a giant crab stirring the ocean to cause tidal changes.
Other myths describe the Milky Way as a cosmic water wheel that fills or empties oceans when turning.
Though the Bible doesn't mention tides, marine scientists suggest Moses parting the Red Sea may relate to extreme low tides exposing seabeds. Tides also inspire poetry like Spring river tides meet the sea, moon and tides rise together. Verses like August 18th tide, magnificent, dancing under heaven. Today's Tides explains lunar-solar interactions, creating ocean surges and showcases global tidal wonders. Author Jonathan White, born on Southern California beaches, holds deep ocean connection. After college, he built an 8-meter sailboat, becoming renowned navigator, surfer, writer, and ocean conservationist. Having sailed oceans for thousands of kilometers, he once ran aground during ebb tide. That sparked his tidal research. White blends history, oceanography, environmental science, and travel to reveal tide's rhythmic beauty and our millennial coexistence. All right, I'll explore the book's core through 2 questions. First, how tides form. Second, how we coexist with tides. First, let's examine how tidal phenomena occur. As we know, tides primarily result from lunar gravity. Oceans bulge toward the moon, causing high tides. Simultaneously, Earth's opposite side experiences high tides from centrifugal force. For example, when the moon is over Shanghai, the East China Sea sees high tide levels, and simultaneously, seas near Argentina and Uruguay on the opposite side of Earth also experience rising tides. How can we understand this? Imagine filling a round balloon with water, then spinning it horizontally like a hammer throw while holding it with a rope. You'd see the balloon turn oval. The end tied to the rope bulges due to the pull, and the opposite end also bulges from centrifugal force. Over 70% of Earth's surface is ocean, which undergoes similar deformation from gravity and centrifugal forces that trigger tides. We collectively call these tidal forces. Since Earth's seawater volume is constant, areas with strong tidal forces experience high tide, while those with weak forces see low tide. Therefore, typically, the same sea area has 2 high tides and 2 low tides per day. Also, as the moon orbits Earth, moonrise occurs about 50 minutes later each day, so tide times shift by over 50 minutes daily. So the moon is the primary factor influencing Earth's tides. Compared to the moon, the sun is farther away and exerts weaker tidal forces, but it amplifies or diminishes the moon's tides. Around the 1st or 15th day of the lunar month, Earth, moon, and sun align in a straight line. The combined forces of moon and sun create higher than usual tides, known as spring tides. Tides aren't just influenced by celestial movements. They're also affected by factors like topography, monsoons, ocean currents, and rainfall. These elements combine to create diverse tidal landscapes. First, topography affects tidal range, the difference between high and low tide levels. Different seabed topographies give seawater distinct natural oscillation periods. Every object has one. For a sea area, it's the time for a water vibration to travel from one side of the seabed to the other and back. The Pacific Ocean's natural oscillation period is about 24 hours, the Southern Ocean about 30 hours, and the Atlantic about 13 hours. If we liken the Atlantic to a bathtub, waves slosh back and forth, with peaks first forming near France in the north. 13 hours later, the wave peak appears at the southern coast of Argentina. How to understand this? If an object is subjected to external forces whose vibration period matches its natural period, resonance occurs, greatly amplifying its movement. For example, bridges have natural vibration periods. Soldiers mustn't march and step across bridges because synchronized footsteps matching the bridge's period could cause violent shaking or collapse. For ocean areas, the gravitational pull of the moon and sun acts as this external force. When a sea's natural oscillation period aligns with the moon's gravitational cycle, it resonates with lunar tidal forces, creating higher tidal ranges. Take the Atlantic. Its 13-hour oscillation period closely matches the moon's 12.47-hour cycle, so many areas experience large tidal ranges. Canada's Bay of Fundy has one of Earth's largest tidal ranges, reaching 16.6 meters. Mont Saint-Michel Bay in France has tides up to 13.7 meters. The renowned Mont Saint-Michel Abbey stands on a granite islet in this bay. At sunset, when the moon rises, tides surround the abbey from all sides, leaving only a narrow causeway. The speed of the rising tide between the abbey and mainland is astonishing. Locals describe, once water covers your feet, within 2 minutes it reaches your waist and sweeps you away.
Historically a pilgrimage site, many pilgrims were engulfed by sudden tides at Mont Saint-Michel.
Modern guidebooks warn visitors never to wander without guides. Unlike Fundy or Mont Saint-Michel, the Mediterranean, though Atlantic connected, has minimal tidal ranges, often under 0.5 meters. This occurs because the Mediterranean connects to the Atlantic only through the narrow Strait of Gibraltar. Its distinct 24-hour oscillation period differs greatly from lunar cycles and Atlantic's rhythm, reducing tidal effects. So, some seas with 24-hour periods resonate with solar tidal forces. Solar tidal forces are weaker than lunar ones. Although the tidal range in these seas isn't huge, it changes how tides behave, sinking more with the solar cycle and rising and falling once per day, called a diurnal tide. The tides in China's Beibou Gulf are a classic example of diurnal tides. Besides affecting tidal range, unique estuary shapes can trigger tidal bores, also known as wave tides. Typically, during high tide, seawater floods into narrow river channels, causing water levels to surge suddenly and form big tidal waves. Take the Qiantang River tidal bore, for example. Its estuary has gentle, trumpet-shaped terrain that narrows upstream like a funnel. When the East China Sea tides rise, seawater easily flows back into the river, rushing into the Qiantang's narrow upstream channels, and with sandbars on the riverbed forcing the water to leap upward, it jumps higher and higher to form massive waves. And for many reasons, there are over 100 tidal bores worldwide. Like the Qiantang River, estuaries with tidal bores are usually trumpet-shaped.
The Amazon River estuary in Brazil has tidal bores up to 3.7 meters high, felt hundreds of kilometers upstream. And there's also the tidal bore at France's Seine estuary.
The Severn bore in the UK was historically destructive, but human activities caused sediment buildup, blocking seawater and making the tidal bore disappear.
Among all tidal bores, none match the ferocity of the Qiantang River tidal bore.
While most coasts take 6 hours for tides to rise, the Qiantang River needs just 6 seconds, like a magician waving a hand, and the tide descends from above.
A water wall, at least 8 meters high, surges like a dragon, moving upstream at 10 meters per second with a deafening roar, only fading 160 kilometers upstream as it waits for the next tide.
Oh, in water margin, the hero Liu Jishen stayed at Hangzhou's Lue Pagoda, woke at night to sounds like an army charging, grabbed his weapon, rushed out, and found it was the Qiantang River tide. 2,000 years ago, the Qiantang and Yangtze rivers shared an estuary. After they diverged, the great tidal bore became unique to the Qiantang. From the 10th to 16th centuries, spanning the Song to Ming dynasties, the Qiantang's largest tidal bores occurred near bustling Hangzhou. Back then, the tidal bore drew tens of thousands of viewers, and people organized swimming races where participants gambled with their lives, leaping into raging tides with colored flags on their backs, tumbling in the waves. They were called tide riders. Ming Dynasty poet Sun Chengzhong wrote, Advise women not to marry tide riders. The tides claim lives regardless of bravery. After many drowned in tidal bores, the activity was banned. Over time, sediment shifted the Qiantang River estuary downstream. Today's grandest tides occur east of Hangzhou at places like Haiyan, Liancheng, and Yangguan. The Qiantang bore appears twice daily year-round, peaking around August 18th lunar calendar. Why does the peak occur in August? This leads to how monsoons, rainfall, and currents affect tides. In coastal areas with strong monsoons and currents, rising tides combine with winds to create massive waves, forming surfing paradises. Mavericks at Half Moon Bay, south of LA, and Jaws at Maui, Hawaii, are surfers' favorites. In August, southeast monsoons over the East China Sea boost the Qiantang's upstream surge. Combined with heavy upstream rainfall increasing river flow, it clashes with incoming tides to create massive bores. But why August 18th instead of August 15th when solar lunar gravity peaks? The reason is tidal friction. Tidal friction, rubbing between moving water and seabed, delays peak tides after maximum gravitational pull. Like pushing a swing, force application and peak height aren't simultaneous.
This delay typically takes 2 to 3 days, hence the August 18th peak.
Global tidal peaks similarly occurred 2 to 3 days after maximum gravitational force. Notably, tidal friction also gradually slows Earth's rotation. Scientists estimate it lengthens each day by 0.2 seconds. Fossil evidence suggests Permian-era days 250 million years ago were only 22 hours long. All right, that concludes part 1. Tides aren't just shaped by celestial bodies, but also by terrain, rainfall, currents, and more. Note that when we talk about tides, we usually mean ocean tides, but lakes and rivers also deform under lunar gravity, creating tidal effects, though they're tiny due to smaller water volumes. Tidal effects become more noticeable in river estuaries and ocean-connected lakes, since they're directly affected by sea level changes. For instance, along the Yangtze River, water levels fluctuate periodically for over 500 kilometers downstream from Chizhou and Y, influenced by East China Sea tides. Additionally, tidal phenomena occur in Earth's gases and solids too. Atmospheric and soil densities undergo subtle changes. In maximum tidal force zones, the crest can bulge up to half a meter. But atmospheric and solid Earth tides are imperceptible without precision instruments. Having covered tidal causes and influencing factors, let's explore the book's second question. How do humans coexist with tides? Tides nurture life. One theory even suggests life originated in intertidal zones, shores exposed at low tide. The ebb and flow generated amino acids essential for life in these zones. 3.5 billion years ago, these amino acids evolved into cells, life's building blocks. Since ancient times, humans have depended on coastal living. When tides retreat, the submerged coast, the intertidal zone, emerges. Shellfish, crabs, and marine life here provide vital food, but tides offer far more than sustenance. I'll discuss coexistence through utilization and management. Starting with utilization, we'll focus on tidal energy. Historians believe tide mills existed in ancient Rome, harnessing tides to grind grain. By the 17th century, European tide mill technology peaked, with over 1,000 along coastlines, 40 clustered near Portugal's Tagus River estuary alone. Tide mills worked simply. Build a structure at the estuary, construct a dam to form a reservoir. At high tide, open valves between the reservoir and estuary, and water rushes in. When the tide reaches its peak, close the reservoir valves. After ebb tide, the water level difference between reservoir and estuary drives wooden water wheel blades to rotate and perform work. In modern times, tidal energy also generates electricity alongside other clean energy sources. Tidal energy has unique advantages. Solar plants are affected by cloud cover, wind farms by unpredictable wind strength. But daily tidal movements are predictable, allowing tidal plants to deliver stable power output. The world's largest tidal plant is France's Rance Tidal Power Station, operational since 1965, with 240 megawatts capacity, equivalent to a major coal plant. China was among the earliest adopters of tidal power stations. As early as the 1950s, the first tidal station was built in Qiantang province. Traditional tidal plants like Rance operate similarly to tide mills. Dams create reservoirs using water level differences, but large-scale dams disrupt coastal ecosystems. Hence, in recent decades, tidal stream generation, harnessing tidal currents directly instead of water level differences, has gained popularity. For example, installing underwater turbines along coasts allows incoming or outgoing currents to spin them for power, similar to underwater windmills.
Still, tidal energy utilization is just beginning.
2013 statistics show only 10% of global energy came from clean sources. Within clean energy, tidal power accounted for just 2%, leaving vast potential untapped. Moving from utilization to management, tides also bring disasters for coastal dwellers. For instance, tidal flooding submerges land, a phenomenon called marine transgression. Facing transgression, some communities live in tidal zones awaiting low tide. In Central America's San Blas Islands, Panama, hammocks are household essentials. When tides rise, hammocks provide dry shelter. This laid-back approach is rare. More commonly, people build seawalls against tides. 4,000 years ago, Himudu people near the Qiantang River built China's earliest seawalls, using mud and straw, called haitang, to prevent tidal flooding. For millennia, Qiantang's haitang have been maintained and reinforced, ranking alongside the Great Wall and Grand Canal as China's three historic mega-projects. Haitang management was critical during the Qing dynasty. Officials were personally responsible for their section's upkeep. Failure meant punishment extending to family members, even death sentences. Recently, global warming, raising sea levels, plus extreme weather like increased typhoons have expanded tidal flooding globally. So how should we coexist with tides amid flooding threats? Venice, Italy's water city, offers insights. Venice sits within a coastal lagoon, a semi-enclosed lake separated from the sea by sandbars or reefs. High tides connect lagoon and sea. Low tides isolate them via exposed barriers. Built on water since the 5th century, Venice has always suffered tidal inundations. With rising seas, streets and squares flood. Some homes get waterlogged living rooms 5 to 6 times yearly. A 1966 flood submerged nearly every street. At St. Mark's Square, Europe's finest drawing room, water reached 1 meter deep, peaking at a record 194 centimeters citywide. Venetians have love-hate relationship with tides. They're as integral as auroras to Finland. Tourists sip cappuccinos in ankle-deep water, finding it charming. Ending tides would strip Venice's soul, yet locals dread waking to flooded homes and post-ebb sludge cleaning. After the 1966 flood, solving Venice's tidal flooding became urgent.
Initially, opinions split. One faction favored non-intervention, accepting minor tidal nuisances and using pumps to drain water.
They believed, if we respect nature, nature respects us. The other faction proposed engineering solutions, steel and concrete seawalls to block tides completely, but wall breaches would be catastrophic, and breaches were inevitable. Ultimately, Venetians compromised. They'd tolerate occasional flooding in low-lying areas, but floods like 1966's were intolerable. After 30-plus years, Italy launched the Mose project in 2003 between Venice Lagoon and Adriatic Sea. The project features 4 barriers with 78 movable panels and an early warning system. Each 300-ton panel connects via hinges to seabed foundations, normally lying flat across 3 narrow straits between lagoon and Mediterranean. They permit water flow. The warning system monitors real-time weather, water levels, winds, and analyzes data from ships within 160 kilometers. During high tides, MOSE issues low or medium or high flood alerts, via SMS and citywide broadcasts. At level 1 alert, seawater backflows begin. Water emerges from St. Mark's Square drains, flooding the Basilica entrance by 20 centimeters. If you're visiting then, don't worry. Public workers deploy walkways. Street vendors sell cheap plastic boots. Otherwise, Venice operates normally. Low-level alerts occur 30 to 40 times yearly. Experts estimate 5 high-level alerts annually. Only then do Moses' bright yellow barriers activate. Air-injected panels rise, separating lagoon from Mediterranean, blocking 3-meter surges. In July 2020, the approximately $6.05 Mose barriers passed final inspection. Additionally, Venetians built buffer wetlands from dredged silt to absorb tidal impacts. The MOSA project, combined with environmental initiatives, adapts better than plain concrete walls, fighting tides while coexisting with them. Venetians' experience epitomizes human-tide coexistence.
Oh, tides are like the ocean's breath, always with us.
Our exploration of tides will continue. All right, that wraps up our discussion on tides. Reading notes are below the audio. See you next time.